Good afternoon, everyone. My name is Mateusz Firuta. I work for Infinera. I came with Pedro Falcao. We are both from Infinera, so hopefully we will present you our offer, what we have in our portfolio, and if you have questions or you need more information, please show up at our stand so we can bring you more information. So first of all, who we are. So we are working for an American company named Infinera. We are based, headquarters is based in California. I came from Poland. Pedro is from Lisbon, Portugal, where we have one of our biggest R&Ds. We have more or less 1,000 customers, more than 3,000 employees, and we are doing optical networking. In the last year, we made $1.6 billion in revenue. We are listed on a stock exchange, so all of our performance you can check on the web. So what we do, we are doing optical networking. So the first question is, what is optical networking? Our job is to move information from one point to the other. So if you want to send some information from Budapest to Szeged, very often you are using fiber, you are connecting the routers over the fiber, and our goal is to put as much information coming from those routers or maybe some other equipments like video cameras, SDH, old equipments, over that fiber. So our goal is to put more and more data on it. How we are doing this, if you compare standard transportation, so our cars, and optical networking, first of all, you need engine to drive from point A to the other side. We are doing this with our optical engines, where we are tuning with our designed DSPs, optical lasers, and we are doing digital signal processing. It's very fast digital signal processing. There is no other industry in this world which is bringing such DSP speed. So it's telecommunication and optical transporting driving processors to the market, and the fastest processors in this world are coming from optical networking. So we are driving this. If you take a standard Intel, which I got somewhere here, our processor is probably 155,000 faster than the standard Intel processor. We are putting these engines into the transport vehicles. So we got some chassis where we are connecting the fibers, and to those chassis you usually connect your routers. And finally, you need an infrastructure. So you need a road to drive from Budapest to Szeged. And we are using this infrastructure in our world, optical world. These are the fibers, amplifiers, regenerators. This is how we transport the information. We are assessing that 98% of telecommunication traffic is being connected over the fiber. The rest is the copper in the access from the old times, and of course, radio links. And 99% of the internet traffic is being lighted up by the fiber optical communication over the subsea cables. So to summarize, we are moving bits, or you can look at us as a plumbers. We are just under the ground, moving every data you are putting. So every firewall, every router, every cell phone is connected over the base station, and from there is a fiber connectivity. So if you are looking at the Facebook, Google, YouTube, usually you are going via fiber, and there is high probability you are using Infinera networking. So how to save the costs on such networking? First of all, you need to save space. You need to save space in the data center. So what we are doing, we are trying to put the data into really compact form factor chassis. And we can say that we are leading this industry. And in 2 rack units, we can put 9.6 terabit per second. We can make it in 300 or 600 millimeters deployment, depending on the data center requirements. But this is to save the footprint in a data center. In addition, we are trying to save, power. It's very modern those days. My, power bill from my home is getting crazy, and I was told it will get even more mad in July time. So we are trying to save energy costs. Everybody wants to be green, but at the end of the day, this is the bill everybody needs to pay. So we are also trying to do that. And the most important is we are trying to put as much data as possible over the single fiber pair. And we have a record-breaking technology, which is 100 terabits per single fiber pair. This is what we are doing, okay? We call it Super C. So the guy who is, showing the chest is the Super C hero. But there is also Super L hero. I will tell you this in the next few slides. So what we are doing, first of all, not every customer requires such amount of data. So we are trying to be really compact and put a proper amount of rack units for the customer, so we can really scale from the small through medium and large chassis. If you look into the large, the Super C hero, in this rack, we need 12 rack units. And on those 12 rack units, we can terminate 144 lambdas, which are coming from 8 directions. So you can imagine you have a big network in Hungary, and you have an 8-degree ROADM. So you go to the Győr, you go to the Szeged, Veszprém on the Balaton, and you terminate the traffic incoming from Romania, Vienna. So you need different directions. And each direction requires specific card, and from each direction, we can drop 144 lambdas. So with the recent technology at 1.2 terabit per second per wave, we can terminate 173 terabits per second in 12 rack unit device. So it's really a very modern, very compact solution, allowing to achieve really record-breaking results and save money on cost in a data center, because you need to pay the rent in a data center. The Super C and Super L, what it is. If you look into the infrastructure, so on optical side, it was, amplifiers, regenerators, etc. You can compare it to the road. And like in a radio systems, when you were listening to the radio frequency modulation, there is some space which each channel is using. So in the past, we started in mid-90s, in the latest century. Those days I was at school learning telecommunication. So we had 3.2 terahertz of spectrum. And the C-band, which is right here, is allowing to achieve very low attenuation in the fiber. So you can cover the bigger distance. You can go more without regenerating the traffic. So 3 times between 95 and 2008, the spectrum was increased by 25%. However, in more or less 2010, 2011, we started something what we call coherent revolution. So we introduced a new way to deliver transmission using coherent technology. And thanks to this, we could really quickly increase the capacity of each channel. So there was no need to gain the bandwidth again in the Super C. And if you look from modulation perspective, the 100 gigabit per second was modulated using QPSK modulation. Then 200G, we had 16 QAM modulation. Then we had 32 QAM modulation. Finally, we got 64 QAM modulation. And once we introduced the 64 QAM modulation, we found out that we can produce 256 QAM modulation, but it will have some penalty in attenuation, which will be 6 decibels, which is 25% of the power of the signal will be eroded. So you will not go from Budapest to Frankfurt, but you will terminate your signal in Győr. And there is a problem because that modulation will not bring such a value. So you can see the saturation of the total usage of the fiber. Yes, we are still growing, 40, 100, 200, 400 gigabit per second, 800, and we go beyond 1.2 terabits per second and 1.6 terabit per second, but this is per single wave. If you look at the total fiber capacity, there is not a huge gain because the 16 QAM modulation is just gaining the capacity of single channel and the fiber capacity is saturated. So what we decided to do at Infinera, we introduced something what we call Super C and Super L. So in 2023, so last year, we introduced the Super C band, and the next year we will introduce the Super L band. Those are the heroes. So what is happening, we are simply extending the bandwidth of the C band. If you remember, I said we had 4 steps between 1995 and 2008, 25% increase in the bandwidth. And now we are extending from 4.8 terahertz into 6.1. That said, we can achieve over the Super C band the record breaking again. So we are using 1.2 terabit per second transponders, but over the Super C band. And using 1.2, we can achieve 55.2 terabits per second over the single fiber pair. And if you take 1.6 tera, so much faster transponder, but only in the C band, not in the Super C band, you will achieve 44 terabits. So the Super C will provide 25% more capacity over the single fiber pair, which is very important because the most expensive in the transport industry, this is the road. It's not easy to build a highway. It's easier to change the car than to build the highway, right? And the same is with the fiber. You need to put the new fiber into the ground. It is taking cost. So we can save a lot of money just introducing the Super C hero. Once we will finish with the C band, we can think about the L band. So if you build a network, you got the transponder here, you got injection point, very often it's a ROADM, it's a RD32 card, and in the middle you got the amplifiers. Those ROADMs, amplifiers, and transponders, they are tunable in a C band or Super C band. Once you will inject 55 terabits per second, then you need to expand with this bandwidth, and you are adding something what we call Super L band. So the Super L band will extend the capacity of the fiber, almost doubling it. So we will add inline, in service, without traffic impacting, we will add another ROADMs, another amplifiers over the same single fiber pair. And we will simply double the capacity of that link. So with that, using the Super C and Super L, the total fiber capacity will be 100 terabit per second. And this is really unique. This is the most modern network. There are customers. I'm coming from Poland. They are very interested in this solution. There are also customers in Hungary who are looking into this. People like Orange, Vodafone, Liberty Global, they are really looking into this and they want to deploy it heavily because very often they make business with Google's, YouTube's, over-the-top service providers who require such huge capacity. So they are building dedicated networks just for Google, for example, in Warsaw, in Sofia, or in Budapest. So this is where we are, and this is how we are making this business. So the technology I am describing to you is a brand new. As I said, Super C was introduced in 2023, and we are right now introducing CHM7 transponder, which is made with our own DSP, which is done in 5 nanometers technology. And next week in San Diego at OFC conference, it's Optical Fiber Communication Conference, we will present this lab. So we will take few of our chassis, including the transponders, and we will run it over few hundred kilometers of fiber, which we will have at the conference, and we will show the Super C band, just transmitting the latest technology. In the same time, for the access, we will use Juniper routers. We are partnering a little bit with them from the technology perspective, and they are also using our pluggables. So if you are thinking about IP over DWDM solution, you will buy the router and you will buy optical pluggable, and it's very likely you will buy the pluggable coming from Infinera. And we are presenting this old solution next week in San Diego. So that was how we can save the cost in optical networking in a backbone. Now let's look into the access and aggregation. What exactly we are going to present with the Juniper next week. So if you imagine how coherent technology is done in optical, you are looking into the whole spectrum. Those are the pictures. The 3 pictures are taken from OSA, which is Optical Spectrum Analyzer. And you are seeing here waves. So what we did, if you look here, this is single wave, which is built with 4 subcarriers. So each signal, it's like in radio, it's on TV. Every signal from the signal analyze, it was one of the worst course at my university, I remember that. It was terrible. So every signal is having its own subcarriers. And what we did, the first generation was what we call ICE4. ICE is our infinity capacity engine. This is the engine which we are putting into our cars to drive transmission from one point to the other. So ICE4 was our 4th generation of the processor, but it was the first generation which was using so-called Nyquist subcarriers, which are coming from digital signal processing. The second generation of the Nyquist subcarriers was introduced with our ICE6 technology. And here we built one wave using 8 subcarriers. And the third generation is something what we call ICE6. And ICE6 is a pluggable device, so it's something what you can put into your pocket. It's very expensive device, so it's something like 10,000 euro or dollars which you can put into the pocket. So you can imagine the progress we made. On one hand, we increased the capacity and on the other hand, we decreased the space because of very large scale integration, right? So such a pluggable in CFP2 or QSFP-DD form factor is allowing you to achieve 400 gigabit per second over the single wave using 16 subcarriers. So why is it so important and how we can use it? So Mr. Nyquist made really great math analyze for it, which was my nightmare during the student times, I tell you. But if you look at the traffic and how we are building the networks, so over the last 25 years, we were building the networks point to point. So you had a 100G plug talking to the 100G on the other side of the network. You got the 50 gig plug talking to the 50 gig plug on the other side. But the traffic looks different. The traffic pattern right now is a point to multi-point. So you got a data center in Budapest, and you have a customers accessing these data centers, which are sitting in Szeged, they are at Balaton Lake, they are in Győr or Sopron, any other city in Budapest, and everybody wants to have an access to this data center to watch movie, to talk to friends, to screen the Facebook, etc. So we thought, hey, this is really great, and we can do something different in optical networking. So what we did, we decided to use those subcarriers to carry the traffic. So if you can imagine, you got only one coherent transceiver on the far end. You can, using the 16 subcarriers, you can light up to 16 end stations in a different cities, and you can grant 25 gig to each of these subcarriers. So in the middle, you just need to split this lambda, something like we are doing in the PON networks. We are just splitting this. And we decided to do it in coherent technology. So it's not the PON, because PON is very short distance. Here you can achieve hundreds of kilometers. So that pluggable could be in Budapest, and that one could sit in Bratislava or Vienna or any other city. So this is allowing to save a lot of money, because you don't have n plus n, but you have n plus 1 endpoints. So you are saving a lot of money on a capex, but also you are using less power to light up this network. You can, if you need more bandwidth, you can light up another subcarrier and have a 50 gig. Or maybe you need 100 gig, so you will light up another subcarrier, and you will assign this to the far end station. What we are doing also to save those money, we are very often putting this over single fiber. So some customers, they don't have a fiber pair, they have just a single fiber. So what we are doing, we are putting the transceiver on one side and on the far end stations. And in the middle, we are putting the silk correlators, which are changing the dual fiber transmission into the single fiber transmission. So the customers are saving money because they just have one fiber. They don't have a fiber pair. So it's a cheaper solution for them. Yes, they are losing some of the bandwidth, but the cost they save is important for them. And very often what they are doing, they have already existing PON infrastructure, which is single fiber. But the PON infrastructure is a great to deliver transmission for residential customers. TV, internet, these are the guys who are delivering infrastructure for our houses, right? We got the fiber to the home, fiber to the carbon. They are providing this infrastructure. And suddenly, they realize that in one of the Budapest areas where they have residential customers, there is a new enterprise which is building some manufactory, and they require high-speed traffic, high-speed internet. So what they can do, they can inject coherent lambda over this existing PON infrastructure and deliver much more capacity, because PON will give you only 10G. There are discussions about 25G PON, 50G PON, but this is very short distance. That can work over 100 kilometers. So you can really inject this traffic over the PON infrastructure and deliver 100 gigabit Ethernet or even 200 or even more with this solution over PON. And the beauty is that the C-band, which we are talking, this is overlapping XGS PON wavelengths, but 17 waves are free. And you can reuse those 17 waves to light up the traffic and provide more bandwidth to enterprise and utilities, not only the residential market. That solution is very user-friendly. So I'm talking about the waves, I'm talking about the spectrum. What we did for our customers, we gave them tools to let them, first of all, forget about optical infrastructure. There are people who are not interested in optical networking. They only think about routers, switches, firewalls. They don't know about decibels, modulation, 16 QAM, 64 QAM. Those are things which people do not understand. So what we are doing, we are giving them management. We call it IPM, which is Intelligent Pluggable Manager. And we are allowing them to manage the network. So if they have an access only to this plug through in-band management, they can discover, manage, and see end-to-end the whole service. And the beauty of this is that that pluggable sits in a third-party router, and the person who is managing the router is seeing this as a standard ZR Plus solution. And in the same time, the IPM is providing to optical personnel of our customers ability to see this as an external farrent transponder to the optical guys who has no clue about command line interface on a Cisco, Juniper, Nokia router, whatever. So optical team is seeing this as a transponder, and the routing team is seeing this completely as a router with ZR Plus interface. The solution is allowing for dynamic capacity allocations, so we can increase the bandwidth. If you don't need 25 and you require 75 gig, it's easily to be tuned from 0 gigabit per second up to 400 gigabit per second. As I mentioned, this is host independent, and it can tune by itself to the frequency, or I should say the wavelength, because each channel is having different wavelength over the fiber. That solution is being standardized by so-called OpenXR Forum. There are some customers who are joining, like Liberty Global, Verizon, British Telecom, but there are also equipment providers who joined OpenXR Forum because they want to use this solution and they want to put this solution into their own data centers, into their own PON infrastructure or the routers. So the very good examples are Juniper and Arista. There is a Eufy Space, Sumitomo Electric. This is the PON infrastructure vendor from Japan, and they are putting this coherent technology directly into their data centers, directly into their routers or PON infrastructure, bypassing optical networking. And of course, there are some other component manufacturers like Infinera, so Lumentum is a good example. If you would like to join this, I recommend to Google OpenXR Forum. It's for free. You can join there, you can get some white papers, see what's going on, where are the conferences. It's really great technology which is right now lighting up our fibers. So with that, I would like to thank you. I think I'm just in time, 30 minutes, so thanks a lot. Any questions? Okay. I understand I made you speechless. If you have some ideas how to use it, show up at our stand. We got some brochures. Go on. You are asking about compatibility, right? So, very good question. So first of all, I said this is the multi-vendor. So if you have a do you want to use it in a router, or you are asking about optical infrastructure in router? Okay. So there are some router providers who already develop it. So the good example is Juniper. They have it in the PTX already integrated. They are thinking about MXs to be integrated. And there are some other router vendors. Beg your pardon? ICX, yes. This is on the next list. But they started with the PTXs, MXs, and ACXs is coming as well. And we are showing ACXs next week. But it's just the R&D phase. They did not deploy it yet. So there is a problem. If you put the pluggable into the router will see it as an unknown ZR Plus plug, because this is the ZR Plus standard. We just call it XR because we spread it into the point-to-multipoint solution, right? So the problem will be that the plug will be unknown. There are some integration tests which we are making. We made it with the UFI space already. We made it already with Juniper, as I said. We are looking at Sienna routers as well. And Nokia is the next one in a queue with the old Alcatel-Lucent routing solutions. The problem is that you need to have the management of this pluggable, right? This is the biggest problem. So there are two variants for this. You either use something what we call CMIS, which is an interface which is used by us to connect the pluggable with the kernel of the router and allowing us to access this pluggable through the DCN of the router. If the router vendor is, we call it friendly, and they want to deploy it, it's already done or it's under the testings. And I can, if you give me your business card, I can send you the whole list of the vendors who already adopted and in which phase we are. But there are also vendors who are, let's say, unfriendly. They did not decide to do it yet. So the IceX is also having something like a VLAN cross-connect. So you can look at this from the layer 2 switching perspective. And if you assign the VLAN ID to the pluggable, to the layer 2 interface on the plug, and into the port on the router from unfriendly vendor, you have a communication and you can have out-of-band management to this plug. So you can approach it from two different angles. The friendly one is more advanced, it's tested. We have the configuration guides. So we can provide, if you tell me which router you have, I can give you the configuration guideline, and you can through the command line of the router, you can provision this pluggable. But if this is unfriendly, we have a workaround, and this is working in a kind of out-of-band management. The Open Gear guys are coming, they are trying to kick me out. Did I answer your question? Sorry, I don't want to be shot by the guys. If you have more questions, please show up at our stand. I'm more than happy to share with you the list of the routers which are already done, okay? Thank you.